In the second chapter of our course on vehicle dynamics and control, we'll look at the dynamic bicycle model. And we'll start this chapter with a quick review of the dynamics of a rigid body. In a previous video on the kinematics of a rigid body, we've seen how to describe the motion of a body mathematically in space. Now, the dynamics of a rigid body is about the causes of that motion, in particular by forces and moments acting on the body. This review will be divided into translatory and rotatory motion, and let's begin with translatory motion. Let's start with the simplest case of a point mass P with mass m in space, and we let Rp of t denote the position of the point mass in an inertial reference frame, and Vp of t and Ap of t are the corresponding velocity and acceleration. The linear momentum, or just the momentum of P, is defined as the product of the mass of P and the velocity of P, and it's denoted with a lowercase letter p. As we know from our basic class in mechanics, by Newton's second law, we have that the time derivative of the linear momentum is equal to the sum of all forces acting on the point mass P. Or in the particular case where the mass is constant, we have that mass times the acceleration of the point mass is equal to the sum of all forces acting on the point mass P. The set of all forces is typically collected in a free body diagram, which shows the point P free of all physical connections, which are replaced by the corresponding forces that actually act on P. So the free body diagram shows the point mass P with all the forces acting on P. Next, let's look at the translatory motion of a rigid body with mass m in space. Remember that in kinematics, we were allowed to choose an arbitrary reference point of the rigid body. Now, in dynamics, it's important that we actually select the center of gravity of the rigid body. And also in kinematics, it didn't matter which reference frame we chose, but now for dynamics, we need to choose an inertial reference frame. So we let Rc of t denote the vector position of the center of gravity of the rigid body, and Vc and Ac of t are its velocity and acceleration. The main difference to the point mass that we just considered before is that the rigid body now has non-zero spatial dimensions. As a first main consequence of this, the forces acting on the rigid body do not act on its center of gravity, but rather they act somewhere else on the rigid body, as can be seen in this example of a free body diagram of B. And the second main consequence, because the body is not a single point, it now has also rotational degrees of freedom. And such a rotation is of course caused by forces that do not act centrally on the body. Before we get to rotations, however, let's look at the translatory motion of a rigid body. And the first thing to do here is to define the linear momentum or momentum of B analogously to the point mass as the product of the mass of the rigid body and the velocity of its center of gravity. Now, as we see from this example of a free body diagram for the rigid body B, the forces acting on the rigid body generally act on its surface and not centrally on its center of gravity. And therefore, Newton's second law does not apply directly in the case of a rigid body. Fortunately, however, we have the center of gravity principle that can also be formally proved. And it says that the center of gravity of a rigid body behaves just like a point mass, and as if all the forces that are actually acting anywhere on the rigid body were acting directly on this point mass. Hence, we have that the time derivative of the momentum of the rigid body is equal to the sum of all forces acting anywhere on the rigid body. And in case the mass of the rigid body is constant, we have that the mass times the acceleration of the center of gravity of the rigid body is equal to the sum of all forces acting on the rigid body. In the second part of this video, let's get to the rotatory motion of a rigid body. So consider again a rigid body B in space that has mass m, as opposed to the translatory motion where the precise shape of the body doesn't really matter because of the center of gravity principle. For the rotatory motion, the geometric shape of B is important. So for the purposes of the rotatory motion, it is assumed that the rigid body B is given together with its geometric shape, and in particular the spatial distribution of its mass in terms of a density function. Just like for the translatory motion, we assume that the reference point C of the body is equal to its center of gravity, or alternatively, we may also choose a fixed point in the body's frame, which is also a fixed point in the inertial frame. So note that from here on, we'll be working with two different coordinate frames. The body fixed frame, which is drawn in red here, and which has the lowercase coordinates x, y, and z, and the inertial frame in yellow, which has the uppercase coordinates x, y, and z. The spatial distribution of the mass of the body B is assumed to be given by its density function, rho, which is a function of the body coordinates x, y, and z, so that the mass of an incremental element of the rigid body, dm, is given by the density function rho of x, y, and z at this location here times the incremental volume of that little element. In particular, the mass m can be computed by summing up over all of these incremental mass elements of the rigid body, which in other words is equal to the integral over the volume of the rigid body of the density function rho of x, y, and z. In this review, I assume that you are familiar with this type of representation from a basic mechanics class, and also that you're able to calculate volume integrals of that form for arbitrary functions. Next, the so-called inertia tensor of the rigid body B is defined as a 3x3 matrix that we denote with a capital letter theta. Its diagonal elements, which we call Ix, Iy, and Iz, are the moments of inertia, or sometimes called the angular masses, of the rigid body B. And they are calculated via the volume integrals that are stated here. As theta is a tensor, in particular it is symmetric, meaning that its corresponding non-diagonal elements are equal. So this pair is equal, this pair is equal, and this pair is equal. And they can be computed by these formulas stated on the right hand side here, and they are called the moments of deviation of the rigid body be? In some sense, in the rotatory motion, the inertia tensor assumes the role of the mass in the translatory motion, as we shall see next. So let omega denote the vector of angular velocities of the rigid body B about the axis of the body frame x, y, and z. Then, in analogy to the linear momentum, the angular momentum of the rigid body is given by the product of the inertia tensor and the vector of angular velocities of the rigid body. Typically, the angular momentum is denoted with a capital letter L. It is again a vector that generally does not point in the same direction as the vector of angular velocities omega, and that's because we multiply omega with a general inertia tensor theta. Only in very special cases, and you can think about which special cases I'm talking about, will the vector of the angular momentum be aligned with the angular velocity vector. Also, recall that the angular momentum of the rigid body depends on the choice of the reference point C, and that's why we mark the L vector with a bracketed C up here. Whereas if you remember the review on the kinematics of a rigid body, the angular velocity vector was actually independent of the choice of a reference point. By the angular momentum principle, we have that the first time derivative of the angular momentum with respect to c is equal to the sum of all moments acting on the rigid body with respect to c. So, for instance, if we have a bunch of forces acting on the rigid body, as in this diagram on the right-hand side, then the moments of these forces with respect to the reference point C are given by the product of these forces with their corresponding lever arms. Observe that the angular momentum principle is analogous to the center of gravity principle in the sense that on the left-hand side we have the time derivative of the angular momentum instead of the linear momentum, and on the right-hand side we have the sum of the moments instead of the sum of the forces. Again, if the mass, or in this case the angular mass, is constant over time, the angular momentum principle simplifies to this formula here, where theta times the time derivative of the angular velocity is given to the sum of all moments acting on the rigid body. Remember again that the angular momentum principle holds for the reference point C being the center of gravity of the body, or C being a point that is fixed in the body frame and also fixed in the inertial frame. At the end of this review on rigid body dynamics, let's consider some important special cases for the rotatory motion of a rigid body. First, if the body frame coordinates x, y, and z are chosen such that they form a principal axis system for the rigid body, then the inertial tensor is diagonal. In other words, all the deviation moments are zero, and the tensor only consists of the diagonal elements of the moments of inertia ix, iy, and iz. Note that such a principal axis system with three coordinate axes that are mutually orthogonal exists for every rigid body. In particular, if we happen to look at a body that has symmetry axis, like in these two examples here of a cuboid and a disk, then this principal axis system happens to be equal to the symmetry axis of these rigid bodies, as shown for these particular body frame coordinates x, y, and z for the cuboid and the disk here. The second special case that we want to consider is that of a rigid body performing a planar motion or quasi-planar motion in, let's say, the xy plane. So as a consequence of this, the angular speeds around the x and y axis are 0, and also all moments around the x and y axis are 0. Then the angular momentum of the rigid body becomes a scalar quantity that's given as the product of the moment of inertia about the z-axis times the angular velocity around the z-axis. And the angular momentum principle in this case yields that Iz times the time derivative of the angular velocity is equal to the sum of all moments acting on the rigid body with respect to the reference point C, where we have assumed that the moment of inertia Iz is constant. So this concludes our brief review of the dynamics of a rigid body, which we will now use to derive the equations of motion for the dynamic bicycle model, and will also make heavy use of all of this stuff everywhere in our vehicle dynamics and control course.